In this video, we're going to look at two classes of functions, even and odd functions. It's important to note that not all functions belong to one or the other, but we will see relationships between these kinds of functions and integral properties, and so that's why we introduce them here. If we define an even function, it's actually easier to start with an example, and knowing that the word even comes from looking at powers like x squared next to 4, we can imagine sketching, say, x squared. And what we notice about that graph is that it's symmetric across the y-axis, or across x equals 0. There's a mathematical formulation for that as well, which is if I take any point on the graph and evaluate the height, I'm going to get exactly the same height if I went to the negative version of that point. So whatever value I put in for x, if I put in negative x instead, I would get the same value. So there's a graphical way to identify even functions, and there is a mathematical or formula-based way to identify even functions. Other functions that we could list would be things like cosine of x. If we look at the cosine graph, it starts and goes down, but it does that on both sides of x equals 0. Any other power, x to the 4, x to the 8, and also combinations. If we added an even function to another even function, it would still have that same symmetry. Okay, well that's even functions. What about odd functions? Well, this would be an example like y equals x, or y equals x cubed. Y equals x looks like this. Y equals x cubed, we'll use a different color here, looks like this. And they do have a kind of symmetry to them, but it's a little more complicated than the even functions. The way it's usually described is that they are symmetric through a point, through the point 0, 0, through the origin. And what that means is if I picked any point out here, x, and went up to the graph, I would see a mirror image of that over here, but it's as if we took that point and threw it through the axis, kept the same distance and same angle, and I end up at a negative version in the y direction. If I did it on the blue line here, if I look at the cubic function, if I go up to the graph for positive x's, if I went to the same point on the negative axis, I would get a negative version of that y value. As I said, it is a more complicated kind of symmetry to describe. This is where formulas can be tremendously helpful. If I evaluate the function at some point x, and I evaluate the same thing at a negative x value, so the same point but on the other side of the axis, I don't get the same thing back. That's an even function. What I get is the same y value but negative. So we have this relationship that we can use for formulas of odd functions. There are other odd functions as well. Sine of x would be an example where it starts at 0 and then goes through and it goes up and down, and it does the same but opposite as we go for negative x values. Given our point in the course right now, we're interested in how those even and odd functions behave when we integrate them. So take a look at these various integral forms here of an integral from negative a to a. So imagine putting that on our graph here. So over a symmetric interval, if this was an odd function, which of the following integral properties do you think would be true? If it helps, do a quick sketch. Pause the video for a moment and we'll check in shortly. Again, we can sketch something maybe a little more complicated than y equals x. Let's sketch a cubic, or even just something odd that covers that span. What we see immediately is that if we integrate from 0 to a and from negative a to 0, because of the symmetry, these are going to be equal-sized areas. One is above the axis though, so it'll contribute a positive quantity to the integral, and one is below the axis, so it's going to subtract, and because we're going in an exactly symmetric interval size, we're going to have exactly balancing areas here because the function is odd, and so we're going to get perfect cancellation and we're going to end up with a 0 value for that integral. And that's going to be a general property for any odd function as long as you're integrating from some negative value to some positive value that's equal, then the total integral value will be 0 because you're going to get perfect cancellation of positive and negative terms. Take a moment now to think about an even function. Again, we're going to look at symmetric intervals because that's where these are going to be most interesting. Think about what the symmetric interval from negative a to a could be rewritten as if we have an even function. Again, a sketch may help. You can pause the video and then we'll check in a moment. All right, let's take an example of any even function. Let's say something hypothetically like a parabola, which has that important symmetry from left to right, same value at the same x and negative x values. Here, if we shade in the region that's being implied by the integral from negative a to a, what we see is that we get one copy of the integral and a second copy of it. So if we look at this integral here, which is starting at 0 and going out to a, that will give us half of the integral value. And if we want the 0 or negative a up to 0 part as well, we can just take 2 copies of that first integral value. So again, sometimes it's handy to be able to either go from the full interval and cut it in half to get one region that might be easier to calculate and then multiply by 2 when we're done. Or sometimes we're given information about this for an even function and we want to compute the area over the whole interval. Again, this gives us a method for doing that. You'll see some practice problems where we relate or use these properties again in more complicated scenarios, but it always boils down to something that you can interpret with a sketch.